All right, so welcome back. So we're going to start our discussion on normalization. I won't get too deep with it today because this is really just kind of an introduction to the concepts and the why. I realized that we're actually pretty far ahead of where we would normally be at this point. But because of the strangeness of the times that we're in, I just wanted to go ahead and get it out there now, get the discussion going now. Uh, Mostly because I wanted you guys, since working together on a group project when some of you may not even be in the same city is also going to be more difficult than in semesters past. And so therefore, I wanted to be able to open this up to be able to get this out there sooner so that you would have an opportunity to start the process of normalization and understanding that for your own systems, for your group projects. Okay? So the whole idea of normalization, what we're trying to do is we're trying to, so this is kind of what we're going to talk about. Okay. Let's see. Let me skip ahead here. Data redundancy and update anomalies. So what we're trying to do is we're trying to reduce what we call data redundancy and update anomalies. And in a system, sometimes, data might be related to other data, but doesn't necessarily always belong in the same table or in the same class or in the same, what would it be? Entity, relation. We use all these terms almost interchangeably, and they do mean similar things and sometimes slightly different things. But the idea is that if I wanted to say, I want to list, all, I want to list all second year uh, computer engineering courses at this university, which ours would be one of them. And I want to list all the courses, and I want to list their course IDs, and I want to list the name of the course. So like CSE 204 database systems administration. And I want to list all the students who are taking these courses. Okay, and I want to list out their names, and I want to list out their email addresses because I want to, maybe I want to contact everybody who's taking a second year course, even if they're not a second year student. Okay. Now, the thing is that I'm getting data that there's some relationships that exist, right? The relationship between the student and the course exists, right? Because I'm getting the students who are taking the course, right? Right? But the course name and the student name or the student email address, they don't really go together, do they? They don't belong in the same class. They would not go appropriately in the same table. And so what we could do, if you were to maybe put all this into an Excel spreadsheet, is you would end up with a lot of duplicate lines, right? You would end up with not a lot of duplicate lines, but a lot of duplication in certain cells. So you might have database, like for example, just with this course, you would have database system administration show up over 100 times, right? Because we would see database system administration and the student who's taking it, and the next student, and the next student. All right. Now, if we stored all that, if we had like an Excel spreadsheet, if we stored all that in a table like that, we would have a lot of data redundancy, right? We would have database system administration show up a lot of times, right? And we don't like that. That is not a good thing to have in a database situation, because what happens if the university decides to change the name of the class? What if they decide, oh, okay, it's not database system administration, now we just want to call it database administration, or we want to call it database systems, or we just want to call it, you know, relational database systems administration, or, you know, there's all kinds of possible names for this course at different universities. And let's say they change the name. Well, we would have to change the name in hundreds of places, wouldn't we? Right? Now, we could run a simple update statement, you know, where it equals this, change to this, but, you know, that may not be the best way. What would be the best way would be for us to be able to store the name of the course in one place, in one table, in one cell. And if the name of the course changes, we change it in that one cell, and then it changes for every other place that it might show up through a linking. Okay. This is what we call an update anomaly. Is if we were to change the information for one place, but not for another. If the data was redundant, if the data showed up multiple places, and we changed it in one place, but we didn't change it in another, we forgot, we typed it in one place and didn't type it in another, right? That kind of thing. Then that would be an update anomaly where we now have conflicting information. Okay. Another thing that this helps with, that by reducing data redundancy, is we reduce file storage. Now, I know this may not seem all that important to those of you who are much younger than me, right? That you may say, oh, but Hojam, we have like tons of space. We have terabytes upon terabytes of space, all right? And yes, when I was a university student, we used floppy disks. Has anyone ever used a floppy disk? Right? A 3.5-inch floppy disk. Right? Those things had 1.44 megabytes of space on them. Right? I can remember shopping at the store one day and I saw for sale they had a thumb drive and it had 256 megabytes of space. And I remember thinking, that's huge. That's so big. Right? Nowadays, that's like, wait, what? 256? That's it? Like that can store like a picture on it or something. Right? So yes, some of us now, we're so used to having so much space available that we think it's unlimited, but it's really not. And especially because as not only has the space has gotten bigger, that we've also gotten lots and lots more memory space that we can use, the truth is the data has gotten bigger as well, where you have shopping websites that have many more rows and much more data contained in their databases than they ever had back 20 years ago. Okay, so we still need to be aware of reducing file storage. So we don't want a bunch of wasted space just because we have this to use, right? It can also speed up searching. Right? If we don't have to, if we have fewer rows or fewer rows with the same data, then when we go to search, it may be able to speed us up. We may be able to have faster searches that are done. Okay. So I want to go back because I realized this slide came later than I realized. Let me see. Go back. All right. So what normalization is going to be is we are going to use a systematic approach to starting with a relation, to starting with a set of data, and understanding the relationships that exist between different columns, different attributes in our data, and be able to based on the relationships that exist between each attribute, come up with a set of tables, a set of relations or entities, right, that will help us be able to more accurately represent how the data should be grouped, if you will. Okay. All right. So some of the benefits we talked about, so it's easier to access, it'll be faster to access the data and maintain it. We'll reduce those data redundancies and we'll reduce update anomalies. And we will take up minimal storage space, so that we're going to reduce that space on the computer on the database server. Okay, so let's take a look at an example. So here we have three tables, right? Staff branch and staff branch. Now imagine if we said, well, you know what, I don't want two tables because two tables looks like a lot, and really this information kind of goes together. All right, this information kind of goes, let's just call this the staff branch table, and let's just have this table, because notice these two tables, you combine them together, and that's what this is, right? So the staff and the branch table combine together in one location. And you might think, well, this makes things easier for me, right? Because if I wanted to say, let's say just this first guy here, John White. I want to send him a letter. Okay, so I need to know what branch he works at so that I can send a letter to John White, or I need to send a package to John White at his branch. Okay, if I take this first way of doing it, well, I've got to say, okay, John White, he works at branch B005. Now I've got to go pull up branch B005 to look for their address, right? So if we think about this as being two separate Excel spreadsheets or two separate tabs on an Excel spreadsheet, we would have to go look up his branch number, then switch over to the other tab and look up that branch number there to get the address. Okay, that's a lot of extra work on us, isn't it? To have to open up a different spreadsheet or a different tab on the same spreadsheet, right? So that's extra work. All right, so that doesn't seem like a good solution. But this solution here, this is very nice, right? I can go look up John White. I can see his branch address right there. I can just go send him a letter. I don't have to go switching around tabs and looking at different places, right? Okay. Now, the way that I presented this is going to be something that I'm going to say probably a number of times during the next few weeks as we discuss normalization, is that oftentimes what is easier for us is not easier for a computer or a database system. What is harder for us can be easier for the database. Because the truth is, this solution works better for us as human beings because we see all of the data in a nice single location. This solution works better for the database. Okay, this solution would be a better database solution. This solution would be a better user solution. All right. And part of the reason why this would be worse for the database is what happens if branch B005 changes their address. And if we had an Excel spreadsheet and we went in here and let's say that they're not 22 Deer Road anymore, now they're, I don't know, they're 25 Deer Road or 25 Antelope Street, I don't know. So they're changing their address to something, right? And we say, oh, you know what, John White, he's the manager. So, and we go and we change the address in the Excel spreadsheet for this, but we didn't see this B005 down here. And we didn't change it there. So now we have a B005 with one address and a B005 with a different address. So you can see that that would present a problem, right? Because what happens now if I try to send a letter to Julie Lee? If I try to send her something in the mail, in the post, whether it be a package, a letter, whatever, and I send it to 22 Deer Road, it's not going to get to her, is it? Because I did not change that address. I only changed this one here. Whereas in this solution here, if they change addresses for B005, I change it here in this one location, one place, and it automatically gets noted for both John White and Julie Lee because there's just the linking here through the foreign key, primary key relationship. And like I said earlier, the example I gave just now about changing the data here in one place, but forgetting to change it in the same, where it has the same meaning here, that's called an update anomaly. An update anomaly is anytime we change, add, update, set, or delete. So anytime we change, add, or remove data, right? And it could affect multiple rows, but we neglect to get all of them. Okay. So the update where we change data. We could also, where we add data, where this could cause a problem would be what happens if in the staff branch table we add a new staff working at branch B005 and we type in their address wrong. Right. Now we have again two B005s with different addresses, and that could be a problem. Whereas here in this solution, if we just add a new staff person at B005, we don't have to type in their address. It just automatically is there. So here we talked about the types of update anomalies. Anytime we insert, delete, or modify data. So anytime we insert, delete, or modify data, if there's a possibility that the result of that insertion, deletion, or modification could result in two things that should have the same data but don't, then that could be, that's what we call an update anomaly, is if it could happen. It doesn't have to actually happen. We don't have to have conflicting data for the update anomaly to occur. The update anomaly simply means that this could result. So it is a potential problem. Right? Okay. Right. So again, we're trying to reduce redundant data. Right? And we're trying to get rid of update anomalies. So here, make sure you understand this here, that in the staff branch, the single table solution, we had redundant data, we had potential update anomalies, but when we separated it out into a branch table and a staff table, what we got was the branch information, the address for the branch only appeared once for each branch. And so therefore, if there was a change to the address, we only had to change it to one place and it changed for everybody. So therefore, data was reduced. So the overall amount of storage space was reduced. The redundancy was reduced. And update anomalies were reduced. Okay. So that's what we're trying to do. All right. We'll skip this one because I want to go ahead and introduce functional dependencies. I'll introduce this now, but we will come back to this. We will come back to this next week. We'll pick up here next week. Oh, was there a question? No. Okay. Okay. We will pick up on functional dependencies. I'll introduce them this time, but I'm going to pick up on this discussion again because this is the core. This is something you have to understand as part of the normalization process. Okay. The idea of a functional dependency simply is where we're saying we have two attributes, A and B, and one determines the other. Okay. The value, if we know the value in one, we then therefore know the value in the other. Okay. So if we say that A, so one way to read this is B is functionally dependent on A. So B's value depends on A's value. Another way we could say this is A determines B. Okay. There's two different ways to say it. B is dependent on A, or B is functionally dependent on A. A determines B. Okay. So a value in A is associated with one value in B. Okay. A way you can see this in diagram form, there's a set of A values. Each A value maps to a specific B value. That does not mean that one B value determines some A value. Right? So this is, we would call A the determinant, because on the left hand, it's the thing that determines the other. It's the determinant. This is the determined value. So A determines B. B is functionally dependent on A. Okay, some examples. We could say staff number determines position. So if I know someone's staff number, I know what position they hold. Right? If I know the staff number, which determines what? Determines who it is that I'm thinking of, who it is that I'm looking for. I know what position they have. Another example for you. If I knew your student number, I would then know what your name is, what your email address is, maybe what year you are. Are you a first year, second year, third year student? Right. So if I know your student number, I know what your year is. And I want to use year as an example here because it's similar to position, as in terms of you get promoted as you pass courses, but also because another similarity here is, what if I knew that someone was a manager? Let's say I said, I know manager. Do I know which staff person that is? Or let me say this for the other example, for the student example. If I said, in this class, I have a third year student. Who is it? You wouldn't know, would you? If I simply said, I have a third-year student, I want to know who it is. Give me their name. You wouldn't know, right? Because there's more than one third-year student in this course. Right? But if I were to say, I have this student number, who is it? Now you would know, right? If I typed in a student number right now, which I won't, but if I did, if I were to type in a student number, immediately you could tell me what year they are, what their name is, and other things, right? Okay. So that's why staff number determines position, student number determines year. It does not work. It does not work the other way around. Year does not determine student number. Student number is not functionally dependent on year. Okay. And the way we can see that in a diagram form is you could have a manager that could point to multiple staff numbers. You could have a third-year student that points to multiple students. Okay. So make sure that you understand the way that this works, okay? The way that this, and the way that this is written. All right. We'll come back to this one actually, and we'll come back to this one on Monday. I want to go back to this. The way that this is written, if you have a value that if I know this, I automatically know this for sure. Then we draw this with this nice little arrow here. Okay. So A determines B. Student number determines name. Student number determines year. Student number determines email address. Student number determines a lot of things, right? It does not work the other way. Okay. Now, sometimes it can. So, for example, email address. Yeah, actually, email address does determine. Like, I'm assuming that none of you share an email address with other students in the class or other students at the university. Okay. So there are some things that may seem to work the other way. Okay. And we'll talk about what that means when we have a situation like that, where you have a kind of a dual dependency where they kind of work both ways. Okay. But I would say for certain, you guys can all agree with me that student number determines first name, and it does not work the other way around, right? If I know someone's first name, do I know their student number? No. If I had, let's just look at somebody in the code, Murat. Okay, so the first student that shows up on my list in this call right now is Murat. If I said, Murat, what is Murat? Give me a Murat at the university. Any Murat, all right? And I'm sorry if I'm saying your name wrong, all right? Any Murat at the university, what's the student number? Well, you could give me a list of them, right? But what's the specific one? We don't know, right? But if I were to give you Murat's student number, and I would say, give me his first name, you would know, right? You would be able to give me that without question. So if for an A value, there are multiple possible B values, so for Murat, there are lots of student numbers, then there's no functional dependency going that way. If for an A value, there is one and only one B value, then there is a functional dependency going on there. All right. So student number determines name. Student number determines surname. Right? Or you could say it as first name is dependent on student, is functionally dependent on student number. Surname is functionally dependent on student number. Okay. So make sure that you understand how to draw this, how to understand which is the determinant, all right, which is the independent variable, if we're talking science, right? And which is the determined, which is dependent. Because this is one of the core parts of when we get into normalization, when we start talking about how to take an unnormalized data set and be able to normalize it into the third normal form, which is what your project is based on, and into further beyond that as well. Okay. All right, so we'll go ahead and end there for today. It's quite a bit early, but we'll go ahead and end there for today. Does anyone have any questions before we end? Questions or comments? Okay. All right. Well, we'll end there for today. Like I said, it's quite a bit early, but I hope this discussion has been somewhat helpful. And like I said, we'll pick up there on Monday with the functional dependencies, because again, this is such an important part of what we're going to be trying to do here. All right. I'll see you guys in just under a week. And until then, have a good week and have a good weekend.